in compression before the steel reaches its yield value.
Yeah.
This beam has 2.5 times the area of the reinforcement. Therefore, the stress is 2.5 times less, the strain is 2.5 times less, so the neutral axis is much lower. Although cracks have formed, the beam has got quite a high bring to it, probably about 5 hertz or something like that. And the neutral axis is still quite low. The predicted failure load for this beam is about 130 kilonewtons, I think. And at the moment we've reached 100. Okay, Ahmed, if you could pump fairly quickly. Although there are cracks, the cracks are holding together by the elastic tension stiffening of the reinforcement. Whoa, there. Did you notice what the load was?
Around between 175 and 140.
135 to 140 kilonewtons. But the beam failed by itself because the energy in the reinforcement was all being transferred into the concrete, and once the concrete cracked a little bit, all that energy was then stored up and was released. The concrete exploded. The only reason it didn't explode more was because of the hydraulic loading system. As soon as the energy is lost, the pressure comes off. But the beam is now reduced down to 50 kilonewtons. So can you see the difference between that and this one? Don't ever fall into the trap of saying, let's put more reinforcement in the beam to make it stronger. You put the right amount in, you maintain the under-reinforced situation, because if you over-reinforce a beam, you get no warning of failure. And the beam is still intact. The cracks are hardly visible, and it's a very dangerous mode. And the only reason we can control it is due to the hydraulic load system. So in both instances, the groups who tested these beams report on the mode of failure and compare the failure mode with your predicted and your Eurocode values. Okay, now the third beam